Hi, welcome. So in this video, I'm just going to go through how we come up with our formulas for writing equations of lines in 3 dimensions. So I'm going to show the derivation of the formula, and then I'll do another video with some examples, and then we'll wrap up the content for this week by doing some examples of planes in 3 dimensions. But this video is about equations of lines in 3 dimensions. Okay, so the way we're going to do this, I guess I'm going to just draw a graph of what a line might look like first, and we're going to label a bunch of parts of it and then talk about how we use those components in order to come up with an equation. So we're going to be in 3 dimensions. So I'm going to draw my x, y, and z axes here. So I have x, y, and z. And let's just imagine some line kind of cutting through this space. So I'm just going to draw a line here. You can imagine that in 3 dimensions, it's like coming out of the page in some way or something like that. I'll show you a 3-dimensional model later. So let's say we have a specific point on this line. Let's call it A, B, C. And this is our specific point. So like maybe I tell you the point that I want the line to go through. All right, then we can think about any other point on the line. So I'm going to think of this as like an arbitrary point. It's just some other point on the line. So we'll call it x, y, and z. It could be any x, y, and z, so that's why I'm just using those variables. So this is an arbitrary point. And actually, while I was writing that down, I realized I want to call this specific point something different. Apologies for that. We're just going to get some different variables that'll help us out later. Let's do x0, y0, z0. So this is just like the initial point we are starting with. It's just some point. I just think it'll be easier to do this rather than using the a, b, c. Okay, so we have a point we're given on the line and then an arbitrary other point. And the other thing we're going to have is a vector that's parallel to the line. So we could just have a vector that's pointing in the same direction. It might not be on the actual line. It could just be in standard position, but it's just a vector that's parallel. So the main thing here is that we are given a point and we're given a vector that is parallel. So this means it would have the same direction as the line. Okay, so given this information, we are going to write an equation of a line. And I actually like to think of it as modeling motion. So there's going to be some time element here. So you can model lines without time. This is just the way we usually start to do it. So this means that the equation we come up with will depend on time. And when we say it depends on time, I like to call it a parameter. So this is where that parameterization, that phrase comes in. So this means that we just have some time element and it's changing. Okay, so far I'm just kind of setting the scene. We have a point on the line, we have another arbitrary point on the line, and then we have a vector going in the right direction. So this is the information we're going to need to come up with an equation that models motion along the line. And that motion along the line is just going to help us get the equation for the line. So let me copy this image and I want to talk through some more components of it. I'm going to put some more information on there. Okay, so let's say that we draw some vectors that are going to the points we're looking for. So because we're doing vectors to help us do everything, I need vectors going to these points. So I'm going to draw a vector going to my specific point, and I'm going to call it R0. It will sort of match the XYZ there. So my R0 or R0, not is just like another way to say 0. So R sub 0 points to our specific point. And with the way it's written, because this is in standard position, the tail is at the origin. This has the form x0, y0, z0. So it just points at the point. So the vector is just those components which come from the coordinate. Then we're going to do the same thing for the arbitrary point. So I'm going to have this other vector, let's call it r. And so the vector r is going to point to any point on the line. So that xyz is any point. So this points to any one of those points. All right. So while we're doing this, just try to keep in mind our whole goal is to come up with a vector that represents the line itself. So that's why we're kind of building these other vectors along the way to help us build the final vector that we want for the line. So here r is x, y, z. That's just to represent any point x, y, z and the vector pointing to it. So given these vectors we've drawn, I want to just kind of blow them up here and look at them big. We have r0 and we have r. And so you might notice that there's a vector going between them that is going to perfectly fall on our line. Oops. Oh man. So this vector that goes between them is going to match up with our line. And we're going to call this vector s, and it's just sort of a placeholder to get us used to what's going on. So you can see here that when we do r0 plus s, we get the resulting vector r. So we're basically adding r0 and s to get r. Let me write that down. So we have r0 or r sub 0, and then we're adding the vector s, which we don't know anything about it yet. I've just kind of labeled it. And that's now equal to the vector r. Okay, so part of our task is going to be to find that vector s. That vector is like on the line, and the line's what we're trying to model. So getting this information is going to be helpful to us. To help us figure out like what's going on with the s, I'm going to open up a 3D graph for us. So let's do that really quick. All right. So the main thing I want to highlight here, I guess before I get into that, let's just make sure we know what parts are which. So the blue vector is the r0 that I had, and the green vector is the vector r. Hopefully, if for some reason those colors aren't working for you, you can compare it back to the graph we had before. And then that yellow vector is my s vector. So what I want to show you is that as we move that point x, y, z, that vector is changing. So I have it set up here to animate. So as we go along the line, that xyz point, that vector s, the yellow one, is changing. It's always pointing in the same direction. Well, I guess it can be pointing backward, but it's always pointing along that line. It's just the magnitude that is growing. So we're going to use some information about this vector and things to help us then like figure out the equation of the line. So let's go back to our graph and I'll show you what I mean. Back to our notes. Okay. So what's going on here is that the magnitude of s, as we saw, is changing over time. So the magnitude of s changes with time. But we have a vector v that points in the same direction as s. So our plan is, since we really don't know anything about s, I just kind of like labeled a random vector on the graph, right? But we do have the vector v. We're assuming we're kind of given that information. It's pointing in the right direction of the line we're looking for. And so our plan is to scale v by some value to get the right s. So specifically, we can scale our vector v by the time factor. So whatever the time is, we're going to have that scale v appropriately to get the vector s we're looking for. So we're going to scale v to get s. Going back to that formula we had r0 plus the vector s, and we said that was equal to the vector r. And here I'm actually going to call r a function of time, since we're seeing that it depends on time. So if we go back up here, we can notice that as time was moving on, that vector r was changing. So actually, I'm going to add it in everywhere here, and I probably should have put it in before, but through 2 iterations of notes, I didn't catch that. So let's put it in all the spots here. And the idea is that that point x, y, and z is now changing with time. So we're looking at different points over time along the line. Again, let me go back to the graph that moves just in case that helps. So if I play this, we have this point xyz, it's moving as time moves, and so that vector, the yellow one, is changing magnitude over time. So we're going to use that time value to scale this other vector pointing in the right direction to match up with this depending on the time. Okay, so what we're going to do is put, instead of s here, I'm going to put time times my v vector. My v vector is something I know, it's what I was given. And then I can insert the rest of my information. My r0 is a vector that points to the point I was given. And then this r of t is my vector that points to the current location on the line. So, okay, this was all just trying to kind of get us ready for me to write for you the sort of vector equation of the line. So the point is here that that vector r points to, it sort of, as it moves, the time moves, it draws the line out. So on our picture, the r would draw the line out. It would start at one side and kind of draw the whole line. And so the vector r represents the line. We say the vector equation of a line and that line goes through a point. Let's call the point x0, y0, z0, or x0, y0, z0, and it goes in the direction v. This is just me repeating that information we started with. This is given by the following formula. So what we're defining here is the equation of the line. We're going to represent it with r of t, and then we were given this point, and then we have a direction vector v. Okay, so when we do this, I'm going to just kind of copy this information down from what we had above. We say the vector r of t, so this is the vector representing the line, this is now equal to what we wrote above. So it's equal to the r0 vector. That's the vector that points in the right direction. So I'm going to write that here. r0 is equal to the vector pointing at the line. So sorry, that wasn't quite right what I said before. r0 points to the point we were given. Okay, and then we add it to this t times v. And v is that direction vector. That's the vector that tells us the direction we are going. So as long as we have a point on the line, that's the r0, and we have a vector that is in the same direction we want the line to go, we can come up with the equation for the line using this formula here. Okay, so this is a vector. The solution is a vector since we're adding one vector plus the scale of another vector. And we have another way we can do this. So because it depends on time, we can also write a line as a parametric equation. So I'm going to show you that to end this video, and in the next video I'll do some examples with this. Seriously, it really isn't quite so complicated when you're actually doing the example problems. I just really want to like explain where this stuff comes from, because otherwise it feels like it comes out of nowhere. And maybe once you've seen this, it still feels like kind of confusing, and that's okay. But the idea is that you at least sort of have a sense for where these things are coming from in some way, that maybe in the future you could go back and try to work through those ideas more thoroughly. Okay, all right. So our next task is that we are going to write a line as a parametric equation. So we can also write a line as a parametric equation. So if you haven't seen parametric equations before, that's just fine. I like to think of them as like basically replacing the x, y, like the variable. So this case it's going to be x, y, and z. We sort of replace them with t. So we have like one variable t that we do the proper things to then represent the x, y, and the z positioning, or like the movement in terms of vectors. So really, parametric is just taking the parameter t and it's putting that as the variable. So that's the thing that's changing now. Okay, I promise it won't be too bad. So let's say we have a point. So this is a lot of repeats from what we already have. I'm just going to rewrite it. So let's say we have the point x naught, y naught, z naught. Okay, and we have a vector. This is the same from before. We're going to have the vector v. And this time I'm just going to give it some variables. So let's say it's a, b, c. So it will have values there, right? It's like representing some movement in some direction. But let's just say ours looks like a, b, c to make it as arbitrary as possible. So then we can do the vector equation. So we're going to start with the vector equation. We're going to start with the vector equation and then get our parameterized equation. So then we have, let's look, we start with the r vector. We say that's equal to r naught plus t times the v vector. So I'm going to substitute these things in and we're going to get a new equation at the end. So something new to look at. So our r naught is x naught, y naught, z naught. And then we're going to add it to the parameter t times my vector v. So my vector v is a, b, c. And now I'm just going to do some of my vector operations to put this all together into like one vector. So I really have x naught, y naught, z naught, and that's being added to, I'm going to distribute that t into each each component. So I have a times t, b times t, and c times t. And now adding the vectors together, we can put the x components together. So I have x naught plus at. Then the y components are y naught plus bt. And the z components are z naught plus ct. Sorry, ct. Okay, so this vector, we're going to use this to come up with my parameterized equations. So this first component is x, the second component is y, and the third component is z. That's how we've defined the vectors to work, right? They have an x, y, and a z component. So what we're going to do is now write these as equations. So I have x of t equals x naught plus a times t. I have y of t is equal to y naught plus b times t. And then I have z of t equals z naught plus c times t. So these are now three equations, and they are parametric equations because they're all functions of t. Well, it's not functions, but they're like, they have inputs of t. And so these are parametric equations of a line. So really, these are just like two different ways to write the same things. We're just like writing it differently. So maybe we want to just look at the x, y, and z's sort of separated out, or maybe we want them in the vector format like we did in the vector equation. So you can go from one to the other, it's just that we have two different ways of writing it and talking about it. Okay, so you now have your formulas in order to find equations of lines in 3 dimensions. So in the next video, I'll go through some examples of how we can make that happen. Thanks so much for watching, and I will talk to you in the next one.